concludes the morning session here, but I have a slightly special introduction to make for our speakers, Jeff Bezanson and Stefan Korspinski, who are both two of the core developers of the Julia language that some of you may have heard about, and they asked me to explicitly say that they're not crashing our party. We invited them. I actually contacted them a couple of months ago and said, hey guys, there's a lot of overlap in ideas, but there's also a lot of interesting things that you guys are doing with Julia, and I think it would be a very productive discussion if you came and gave a really technical talk on some of the problems that you're addressing with Julia and some of the approaches that you can take when you have the freedom of a new language. And please come, give a really technical talk, and I'm sure it'll be a very productive discussion. So I'm really happy that they took me up on the offer and that we have them here. So
thank you.
Thank you. So my name is Stefan Karpinski. This is Jeff Bezanson. We created Julia with two of our collaborators, Viral Shah and Alan Edelman, who couldn't be here today, but I think two of us is enough. If anyone saw Travis Oliphant's talk on Numba just now downstairs, we actually have a lot of common goals, the Julia project and the Numba, and we're in the unusual position of being ahead of a Python project in terms of development. So that's a turnaround, but the standard compromise that's come to exist, in which some SciPy and NumPy and all of Python, in fact, is an instance of, is this two-tier architecture to address the compromise between performance and convenience. We know convenience is winning. Everybody's here because they like using a high-level dynamic language to do their scientific computing. But C and Fortran are still the gold standard for performance. So what you do is you end up writing your high-level stuff in something nice and convenient like Python, and you end up doing all the heavy lifting in C or Fortran. So this is pragmatic for a lot of applications, but it does have drawbacks. So for example, we would prefer to write our low-level code in something convenient as well. It forces vectorization. Vectorized code is actually convenient for a lot of linear algebra stuff, but there's also situations where you just want to write a loop. And it would be nice if that loop was as fast as it was in C or Fortran. Actually, you got to stand back too. Sorry. If any of you have written any of the, written internals inside of SciPy or NumPy, there's a lot of complex mediation. You have two type systems, you have two garbage collection schemes, and you have to work between them, and it gets to be it's harder than writing either C or Python. There's some overhead. There's also a big social barrier. So, if you're just a user of SciPy, that's kind of okay because you don't ever have to get into the internals, but it prevents you from getting into the internals. If the internals were also written in Python, you could tinker around with them. You could see how they work. You could understand why something does or doesn't perform well. So these days there are fast dynamic languages. So PyPy is one good example that's pretty well known. You can get Python. There are issues with using Python for scientific computing. It's incompatible with C Python and its APIs, but you can get Python to run fast in a lot of instances. LuaJIT is another pretty famous example. It's an incredibly good fast JIT for a dynamic language. And of course, JavaScript V8 runs very close to C performance on a lot of code. So our question, and one of the reasons why we set out on this project is, what all of these have in common that they took an existing dynamic language that was designed to be interpreted and tried to make them faster. Well, what happened if you took our advanced knowledge, the fact that we now know how to make a dynamic language run fast, and designed a dynamic language to take maximal advantage of that? And while you're at it, maybe we can provide a little additional expressiveness. So this is Julia's approach in a nutshell. We want something that's fast, primarily fast. I mean, that's really the end-all be-all. It has to be compiled speed. Fast, but also dynamic, because that's convenient and it gives you a sense of tangibility. You're actually touching the objects almost. And expressive. So the core design principle of the language is generic functions, which is also known as multiple dispatch. I don't know if anyone's familiar with that. In Traditional OO, you can only dispatch on the receiver of a message. Multiple dispatch, you apply a function to its arguments, and what implementation gets called actually depends on all of the argument types. There's a rich type system. So we expose a type system to the user. You don't have to use it. You can write completely untyped code, and it'll also be fast. But if you feel like talking about types, you can. And the speed allows a lot of Julia to be written in itself. There's a very, very tiny core in C, but it's like 10,000 lines of code or something like that. The rest of everything is just written in Julia, which allows you to mess around with it, see how it works, change it easily. So we use LLVM for code generation, but this isn't a silver bullet. You do need to generate good code for LLVM to work with in order for LLVM to give you speed. If you just generate a very untyped and not very tight code for LLVM to optimize, you still won't get performance. Our type inference is not Hindley-Milner, if that means anything to anyone here. Okay. So, geez, sorry about this. Okay, so one question that may occur to people is why types? Like we like dynamic languages. We don't want to have to mess around with types. We like being able to write code that just takes A and B and adds them regardless, based on their value. And the answer is that there are always types. So even in quote untyped languages, you're actually working with typed values. You just don't have a way of talking about types. And so our approach is to let you continue to write code that doesn't explicitly talk about types if you don't want to, but there are cases where you inevitably end up talking about types, and you see this in NumPy a lot, right? You have typed arrays, and now Python doesn't provide a good way to talk about the fact that something is a double. You end up having to use strings in a weird way to talk about what the type of things is. And this is common in dynamic languages. That's just sort of a general issue. And fast implementations, as it turns out, always have sophisticated type systems because they have to reason about these things in order to be able to generate code that's good. And so one of our ideas is, well, why not just expose that? We're going to have a type system. Why not make it really good and fairly sophisticated? Let the compiler use it, but also let the programmer use it, if they want to. Okay, so here's just to give you a sense of what Julia looks and feels like. Here's a couple of code examples. Here's an implementation of a quicksort function. As you can see, there are no types mentioned anywhere. It's kind of like, like Ruby or Python code would look. A is an array, you have low-high indices, and you just do your usual stuff. And you have, low-level bit twiddling, you have loops. All of this runs at C code. This is our actual benchmark code, and it runs at C speed. Here's an example of something a little more medium level. And this is more medium level because it's more at the level that you would be writing for, say, NumPy or MATLAB, where you have vectorized operations. Create a couple of vectors of zeros. You create some random matrices, n by n. You concatenate them in a couple of different ways, and then you compute some matrix powers and take traces, and you iterate through this. This is also a benchmark we use. This is an interesting benchmark because the objects are small enough that you don't get enough leverage from having using an LA-Pack core to actually get really good performance in NumPy or MATLAB or something like that. So being able to generate good native code all the way up and down the stack is really important for this sort of thing. So here's some high-level code. This shows off one of the the core features, which is multiple dispatch. So you see those colon annotations. That marks the type of something. So this code actually is the code we use to implement our distributed arrays, which we use for large-scale parallel computing across multiple machines. And it begins by synchronizing across the machines. Then you see that spawn at line. Basically what that says is I want you to do this local operation at processor P, and then it calls another copy to. That copy to is something like this bottom function, which is for a local array, and it just does a simple loop. And as you can see, our loops are just implemented fairly simply in Julia itself, and that, that runs at native speed. For this kind of thing, though, you actually want to use something like LAPACK, because they're heavily tuned. So we'll have even another method in there that will be called for things that can run in LAPACK. So I'm going to hand it over to Jeff here. Just put this on.
All right, hello everybody, I'm Jeff. I'm going to take over the talk. So I want to go back a little bit and just say something about this kind of high-level untyped code of the kind you could write in MATLAB or Python. Sort of the thing to notice about it is it's kind of client. It's API client code, essentially. It's basically it's a consumer of definitions. It's using definitions that other people have set up. Like when you have a star operator or a plus operator, there's a lot of complexity and a lot of stuff happening inside those operators. And here you're just sort of using them. You're not really specifying how things work. You're just kind of using it. And so the real difference in our approach is that we pay a lot of attention to mechanisms for declaratively defining how things work, and that lets the compiler piece things together very well. And the key to that, to me, is really the multiple type-based dispatch paradigm. And I think multiple dispatch ends up being kind of clever because it lets you sort of collect a lot of type information that's not redundant information. Because when you put these dispatch specifications on function arguments, it's not redundant information. It's not a declaration. It's not just telling the language that, oh, by the way, this thing is an int. It's a dispatch specification. It's saying when this argument is an integer, call this function. So it's not redundant. So that way I find, psychologically people sort of don't mind writing these types because it's sort of telling the system how the thing works. It's not redundant information. So for example, here's how we specify some of the behaviors of some of our operators, like plus on 2 int 64s. It basically, comes down to, a machine instruction, effectively. So that's how, and we just have lots and lots of definitions like this. It's all written in Julia. And then we also have, for example, a numeric promotion mechanism. It's also defined in Julia using, type-based dispatch. And that's basically, you give it 2 numbers and it promotes them to a common type and gives you something back. So then you can do things like this, where I can say if I have plus on 2 numbers and I only know that they're numbers, I can try promoting them. I can try calling promote and then trying the plus again. So you can, define up all of these normally really low-level behaviors. You can define up out of this whole dynamic dispatch scheme. And this gets fancier. So if you want to start specifying some more fancy behaviors, for example, we have a whole universe of various arrays, and then there are some of those arrays that are special in that they are supported by libraries like BLAS and LAPACK. They have to have a certain memory layout, right? So we'd like to describe that situation. So we can start by defining a type that basically encompasses the element types that LAPACK supports. And then we can also define a type that's strided matrices. And that basically means either a contiguous dense array or some kind of a subarray of that. And we have this type subarray that actually was somebody else wrote. Neither of us was the one who wrote it. It was a summer student, actually, who implemented it. And it's basically a type that just does index transformations on top of some other array. So you can put any other kind of array under it, and it'll view a part of the array in a certain way, and it'll handle the index transformations. So it obviously isn't going to work with everything because certain kinds of arrays have extremely different layout and access time characteristics and that sort of thing. So if not every level of your abstraction stack there knows about those things, you can hit performance road bumps and things like that. But these things will work well on dense local arrays, and you can put a distributed array underneath it too, and that will usually work pretty well. as well. And so the things just compose together like that. And so all the operations on the subarray are just written basically as functions that transform indexes. And so but the compiler can see all of those, and when it can prove what the types are, it will put all those together and inline them, and you can still get pretty fast implementations a lot of the time. So having defined those kinds of types, I can now make a definition for star operator, where when I have some element type that's supported by LAPACK, and then I have a strided matrix and a strided vector, then I know that I can call the BLAS GEMV function in there. And so that basically encompasses that declarative information. And so this, it's convenient for you because you just have to say, when I see one of these kinds of arrays, please do this, and it's good for the compiler because when it knows what the types are, it can just dispatch directly to this without going through any kind of, runtime if statements or something. Similar kind of thing for memset, where if I've got a fill operator, and if I happen to have an array of bytes and some integer, then I can call memset. And so this is the full implementation in this case. So the advantage of this is the kind of abstraction where you can build things, really people independently of each other, and the compiler composes them together effectively. And we've had people come along who are relatively new. I mean, the whole thing has only been announced for about 6 months, so pretty much everyone is a new user. And people have come along and added really big, interesting chunks of functionality, and it didn't take that long. Like somebody added bit arrays where they're packed 1 bit per element. Someone just implemented that, and it drops right in, and basically everything works. And like I said, a summer student wrote the subarray thing. People are working on library for modeling statistical distributions. And there's an R-like data frame that's work in progress. And it's particularly easy, given this sort of axiomatic style approach of defining things up with these all argument signatures. It's easy to change really low-level behaviors that are really difficult to change in other systems, like the arithmetic behaviors, like I was talking about, and adding new types that are essentially scalar representation. We have a feature that lets you define a type whose representation is just a bit string. So as an example of this, this is something that actually happened. At one point, we were talking to people, and somebody pointed out and said, hey, your integer arithmetic behavior isn't really right. You're doing unsigned preserving, and it should be value preserving. This is a change in the way the integer arithmetic works. And we said, you're right, we should change that. And this slide is basically the entire patch. All we had to do was go through our rules for type promotion on integers and just change which types to pick. And this was the entire diff, and then you just hit the button and rebuild the system base image, and you just get that behavior everywhere. That's the whole change you need.
Yeah, so is this on? Yeah, okay. Just to clarify what's going on here, we're basically saying that, if you combine an unsigned integer like an uint 16 with an int 64, now, previously we were saying we want an unsigned number, now we get a signed number. We just kind of change that systematically all over the place, and this is the entire change. So.
Okay, performance. These numbers are on our website, and this is not something to read too deeply into. This isn't a be-all and end-all exhaustive comparison. It really just says one thing, which is that the raw speed of code generation of simple operations in various languages. And R and MATLAB and Octave are kind of way up here. And this is a logarithmic scale, by the way. So, up here we're talking about factors of actually thousands. And it's not application performance. It's just the low-level looping performance. So it's.
You'll note in here that the furthest right benchmark is a highly vectorized thing, the kind of thing that NumPy was made for, right? And Python does great for that, right? Because here you have. It's calling out to a C library and doing a really fast job and not having a lot of overhead. MATLAB also does great. Octave does well. Octave is usually terrible, but Octave does pretty well. So that's the sort of thing that NumPy is great at. If you're doing things like actually just writing in your language, shuffling around numbers, then it becomes much more difficult to get that kind of performance at a higher level. So that's, and interestingly, JavaScript does phenomenally well.
Yeah, V8 JavaScript is very impressive. It's really amazing performance over here. It actually beats us on one or two of these, I think, but we'll see what we can do about that. Okay, so Julia and Python interoperability is something we've kind of started thinking about a little bit. We haven't had time to really thoroughly address it, but we're thinking about it. One thing we want to do is be able to statically compile Julia code into shared objects that you could then load from Python and call through the C ABI. I think one advantage of having a language that's sort of designed with the idea of type inference in mind from the beginning is you can do a better job of getting types without actually running the program. And even if you can't statically type everything, you'll probably get a lot more, and you'll be a lot more likely to be able to get a good static compilation. So that's something we want to do. I think also sharing on disk data formats. I mean, if people have large data sets stored, NumPy and Julia should be able to both access them, and so we certainly want to be compatible with things like that. And we did just for the fun of it, we did quickly try calling libpython from Julia. So we have since we can call C, we can do that.
Yeah, that took me about 5 minutes to figure out how to do, just like looking at libpython, and then it worked. It prints hello from Python.
So probably on top of that, we could, with a little more work, we could make a nicer API within Julia for calling Python things. And well, here's some reactions from people. Some people like it.
Yeah,
I think is that.
We've gotten positive responses. Interestingly, our users seem to really like Julia. MATLAB users do too. I think SciPy users are pretty happy with what they have, but there's that whole two-language thing, which makes it, if you need to get into the guts of something, SciPy is more difficult. Julia maybe makes it easier. So, any questions?
And since